Is my audio and video coming through clearly?
Yep.
Great.
Sounds
Great. So I am finishing up a postdoc at IU Bloomington, and I'm about to start a visiting position at Trinity College in Hartford, Connecticut. Um, the bulk of my focus has been on this magnetic field design for the neutron EDM project in Los Alamos. There are two different efforts, two different approaches that I'll discuss with more focus on the scalar potential derived one. But I will start with a disclaimer that I'm still new to this, and it would really be wonderful for me to hear that there's an easier approach than what I'm doing, or that I've just done something terribly wrong, because that'll save me lots of time down the line. So we can start with a brute force approach using COMSOL and MATLAB. So this is a kind of an animated cutaway looking at 1/4 of our magnetic shielded room and the general problem statement of what we're working with. We have multiple layers of mu metal, of cubic layers of mu metal shielding material, and we want to apply current in some distribution on the inside that innermost shielding layer in order to generate the most spatially homogeneous magnetic field in that cylindrical holding cell at the very bottom. And so this is a problem, it's an optimization problem with, depending on how you've framed it, 7 or so free parameters, where we're looking at the width of the current bands, the current density in each band, and their vertical placement. With all of that, we want to minimize, for example, the volume average of the relative Z gradient of the magnetic field across our central 20-liter volume. One way that we can do this is using MATLAB and MATLAB's parallel processing toolkit. You can spool up, given enough RAM, you can spool up many different COMSOL servers, and each COMSOL can solve a version of this problem coordinated by the master, by the root MATLAB thread, which can then run some parallel optimization algorithm to find, to solve for your current distribution. In doing that, you wind up with this pretty good current distribution, where here we wind up with a spatial uniformity on the order of 10 to the minus 4 per meter. And so this is using square coils, and a later improvement to this by Jared Brewington at Kentucky is actually moving the square coils to octagonal coils, but really optimized using a very similar technique. But here you can see the cutaway of our sample region in the very center, the inner layer of the shielding room, and then obviously the outer layer of the shielding room. But we can see that there's a lot of space between what we care about and where our shielding is and where we actually need to place our coils. And so here, the scalar potential is defined across this entire closed volume. But that's really over-solving the problem that we have, because we only care about our field uniformity in the central sample region. Furthermore, we need holes in the coil surface for our guides, for our vacuum systems, for high voltage, for optics, for just so we can actually build an experiment that we can access and read out from. And so what we really want to talk about is the scalar potential that we're generating at a distance. We're applying the current just inside the magnetic shielded room, but we need a uniform field across the storage cells. And furthermore, because we are working with gaseous mercury and ultra-cold neutrons, we've got two different gas species that are sampling the full volume during storage. And so what we're going to do, or what we would like to do ideally, is calculate and invert some transfer function given a full basis of scalar potentials in rectilinear coordinates, hopefully simulate the Coil response from each component, decompose that Coil response across the sample region, and then ideally we'd like to orthogonalize the response matrix and generate some new linear sum uh, of modes that yields any desired potential function. And so what the code that I've been working on does is it solves for first an idealized scalar potential. Then we extract the windings from that. We add add mu metal, energize the windings, and then solve for the scalar potential across the fiducial volume. Then we decompose that scalar potential across the fiducial volume back into its components. One thing that I came across recently is whether I need to do that projection as a surface or a volume integral. I don't think there's a difference in theory, but for the finite element considerations, I've been doing it as a surface integral and suspect that it would be more stable just getting more mesh points in there, doing it volumetrically. And so my code base, basically, what we do is we build a COMSOL model and then point MATLAB at it and wait, and then specify a field. This is all developed. I've got a public repository that you can see my atomic mistakes and commits. And one major thing that I wanted to handle in code and develop on this is actually a unified, nice way to add penetrations to my surfaces. And what I found was the most robust way to handle that. Where we have a penetration, we don't want any wires because we don't want for wires and whatever's passing through the penetration to interfere with each other. In the scalar potential model, a region without wires is a region with constant scalar potential. And so we can assign the penetration to a fixed value of scalar potential, which we can just directly calculate from the prescribed scalar potential that we want on the overall model. And of course, because there is going to be some discontinuity between the outer surface and the penetration, we also add an annulus that's allowed to float just so that you get nicer winding paths. The next thing that we have to do is we have to generate the contour lines. There are a lot of subtle and, I guess, computationally interesting problems that I would rather avoid of working in arbitrary coordinate systems or dealing with spherical or cylindrical shells. And because for our particular apparatus, we have, we're working inside a cube, I've written my code so that it works for planar faces. As long as we have any arbitrary number of flat faces with a defined interior and exterior, then we can generate the contour windings. We can solve for the contours on each one individually. So in code, we take those three-dimensional planes individually, transform them with affine transformation into 2 dimensions, find the contour lines across the mesh. As long as it's a triangulated mesh, we use a triangular contour method, and then correct the direction of those contour lines. We correct them using the same idea that Michael was just talking about, where we want to make sure that as you move along the contour, the gradient is always facing in the same direction. And so what I do is I generate the contour lines and then check their direction. And if the direction is backwards, then I just reverse the direction of the line. Then when you import that line back into COMSOL, COMSOL respects the direction it uses the ordered direction of the points that you've imported to apply the currents. So you wind up with current lines that are all in the correct direction. And so at this point, you actually have a collection of lines in 2 dimensions that would be ready to build. This figure on the right is meter scale, roughly, just an example of some of these, of 4 of the 6 faces of a test cube with some odd harmonic that I put on it just to stress test my code. The line collections themselves do need a little bit of work to model them robustly. So if the points that come out of the plane contour method are irregularly sampled. And so if you try to mesh them directly, you'll wind up with some meshing surface that looks like this thing on the right, where some of those points are clustered really closely and some are spread out, and that's going to be slow and tremendously computationally expensive to run. Additionally, you have some irregular points that when you feed into the faster interpolation curves, you get these poorly defined, these jagged regions, bad steps. And so the nicest prescription is to resample the contour. And so I have written code that resamples each contour to a prescribed interval. And then you also, because you have finer detail that you need to resolve around the penetration, the code is able to look for points that are near the penetration, split the contour line, and mesh them more finely in this region. So an idea of kind of how this works. Solving takes 20 to 35 minutes or so per basis function on my workstation, which is running a Ryzen 2 16-core Threadripper with a lot more RAM than we need. And as you get to higher order Ls, occasionally you need to add in some hand holding to actually get the mesh to converge and for that model to be able to solve that model. And here we've got an example of the L equals 2, M equals 0 mode coil on a 2.4 meter cube with 12 different penetrations that have some symmetry, but you can see how the windings are automatically being routed around the are being routed around the penetrations. Here's an example of one attempt to invert to actually solve this direct problem with the inverse. And you can see this is a composite coil of from L equals 1, 2, and 3 modes. The dominant contributors here are the L equals 1, M equals -1, and L equals 3, M equals -1 modes. And so some open questions that I'm still working on are, if we're linearizing these low order harmonics at the expense of higher order ones, for a bottle experiment like ours, are there certain harmonics that are suppressed that we can just use to shunt the excess gradient into if we can control that. There's an issue of current density where the higher order harmonic corrections for this experiment are smaller. And so we should be able to adapt the number of windings, the number of contour levels that we're solving for as a function of L directly. For general assembly, it would be nice if we didn't have to wind 6 coils and somehow get access to 6 coils. And so if we restrict the coils that we're allowing them to solve on to certain faces, how do we reconcile that with this technique? And then finally, how high do we need to go with L? Given code, running it on a computer with enough patience, that can basically go arbitrarily high, but there's definitely diminishing marginal returns. And so in conclusion, the code that I have is able to generate manufacturable windings on any oriented, closed-faced, flat-faced, closed surface. Adding these constant scalar potential patches yields reasonable penetrations. Now, some of the downsides is the method that relies on geometric nonlinearities isn't a great candidate for linear transfer functions. Just to say that the direct inverse method that I had attempted over the weekend didn't improve things as I would like. And again, part of why I'm really excited about today's talks is looking for a more clever way to handle the iteration or cancellation of the harmonic contributions. So thank you all for your time. Thank you for my support coming from Los Alamos LDRD and National Science Foundation. And now I'd love any of your questions.
Hi, Austin. I don't have a question, but more of a comment. I tried something very similar with the cylinder, and I also never got it to get, to improve like I thought it would when I would try to do this method. Mine wasn't quite as sophisticated as yours. I had much more hand holding, but I also ran into similar issues, I think. I don't have a way to fix it, but I'm also, I have the same problems.
Yeah, and the initial values I'm getting out they're pretty good. There's not a huge amount of mode mixing initially. So and that might be connected to the relative size of the discretization and how far away we are from the wound surface. That any contribution from adding these wire deformations is suppressed by the time we get into our fiducial volume.